There we-
Okay, so I'm starting the recording now. We're going to the
Okay.
cloud. And you got about 2 minutes.
2 minutes, 2 minutes.
2
2-minute warning.
minutes.
2-minute warning, okay.
Anyone get a Red Sox score before we go in the,
Yeah,
they were
what's going on?
losing, right?
They're losing?
And the last time I checked, it was 1-0 Houston.
Bad deal last night.
Oh, they should have won that game. That was terrible.
It's a lot of zig and zag on these things. You know,
Yeah,
they win
Yeah.
win one day and then boot it the next.
Oh, I know. That's the way it is. That's baseball.
oh, yeah, it's two good teams in different ways. Well, here we are, coming up to 7.
Yeah, I got 6:59 over here.
Well, Marty, we'll give you a cue. How's this? We'll just give you
Okay.
an on-air cue. There you go.
Well, good evening, everyone. I'm Marty Feldman, Chair of the New England section of SMPTE, and welcome to our October meeting. We've got something special for you tonight, and this is a topic that I think every SMPTE member should know something about and possibly participate in, and that is standards. SMPTE, above all else, probably is really a standards-making organization. But it's amazing how many of us don't really know the inner workings of it. And to introduce us to that, I've got someone here who has been involved in it for much of his SMPTE life. He's a SMPTE Fellow. He holds many patents in electronics and in television. And some of you may know him. He's certainly been around a while. He was a pioneer in the development of time-based correctors and other gear that we all use. And his name is David Acker. David Acker, and I probably know him for a good 30 years.
All right, yeah.
I would say probably about that.
I would say.
And he is going to tell. He's a SMPTE Fellow. He's a graduate with a master's degree from MIT, the little college on the river. And I'm going to turn it over to him to tell you all about the development of SMPTE standards. Dave, it's all yours.
Okay, I'm going to share the screen here. We'll put it on this mode here. Okay, can everyone hear me? Okay, I guess I must be on.
Sounds good.
Well, okay. Thank you, Marty, for your introduction, and hello to everyone. I am very pleased to present this program tonight. Before we start, if any of you have any questions as we go along, please do not hesitate to stop me and ask. I don't mind that at all. So we're talking about the development of SMPTE standards. When Paul, Marty, and I and some other section managers of SMPTE New England started to discuss this program at one of our planning meetings, we thought a series of relatively short presentations on standards activities and updates would be appropriate. But in digging further into what to present, it became quickly apparent that a full program session is warranted. So here we are. Going forward here, about SMPTE. SMPTE is an internationally recognized standards organization that provides a variety of vital technical framework to the industry. The society has developed more than 1,000 standards with more than 800 currently in active status at this point, and related documents currently in use by engineering communities internationally. Such standard documents influence nearly every piece of motion imaging content seen and heard by billions of viewers, literally billions worldwide. By providing structure, organization, and interoperability, SMPTE has helped advance the motion imaging industry through all of its major transitions, from the advent of sound and color to the shift from analog to digital formats. SMPTE has been the innovator of some of the most iconic standards for high quality content, as well as those that are facilitating the transition to an IP-based multi-screen world. SMPTE continues to innovate at a rapid clip. Give you a short summary of the presentation that includes why we need standards, the organization and structure function of the organization, and the story of one of SMPTE's cornerstone standards. Was it SMPTE color bars? No. Was it SMPTE time code? No. So you'll have to wait a little while so you see what's going to happen there. From a personal viewpoint, I have a keen interest in SMPTE standards since I worked on the committee starting in the early 70s, and I'm happy to share with you some of my experiences regarding how they are developed. I would encourage all who are interested in the work of SMPTE to learn more by joining the society and taking advantage of their superb website and extensive range and depth of information. It's remarkable how much information is on their site. So the next slide is the question: why do we need standards? Well, standards allow technology to work seamlessly and establish trust so that markets can operate smoothly. They provide a common language to measure and evaluate performance, make interoperability of components made by different companies possible, and protect customers by ensuring safety, durability, and market fairness. The market fairness aspect of it is a level playing field for buyers, so they know what they're basically getting. Where would we be if dealers sold equipment that could not operate with another manufacturer's equipment? For example, one connects a camera to a switcher and it doesn't work as expected. The picture drifts or the colorimetry is messed up. One talks to both companies and they blame each other. Digging deeper, you might find that they're not on common ground regarding signal specifications because there was no standard to define them clearly. You get the picture. That's no pun intended. Continuing on why we need standards. Standards are everywhere and play an important role in the economy by facilitating business interaction, enabling companies to comply with relevant laws and regulations, speeding up the introduction of innovative products to market, and providing interoperability between new and existing products, services, and processes. Enabling standards form the basis for the introduction of new technologies and innovations and ensure that new products will be compatible. Today's key standards include the Serial Digital Interface, SDI, HSDI, and many that followed the initial development of SDI, emerging standards like high dynamic range, the ST2110 for digital video over IP. That is a suite, a whole bunch of connected standards that talk about and govern the video over IP, and the material exchange format, MXF. There will be a lot of more information on the various formats of connections between files that work on the internet coming up. Let's talk about the types of standards that SMPTE produces. There are 4 main ones. There are a few others, but these are the key standards. When people hear and think about standards, they think about just a standard that is basically a basic specification. But there are other documents. The standard defines basic specifications, but also functions necessary to achieve effective interchange among users. Another important document that's produced is called the overview document. I call it a roadmap of documents. If you have a suite of standards such as the 2110 group, then the overview document is a listing of all of the group of standards and what they do. And it's a long list for 2110. So that's a useful document. The next one is called recommended practices. A recommended practice is a document that states some basic specification, but not necessarily needed for effective interchange or connection, but that facilitate the implementation of systems. Examples are conformance requirements or measurement methods, constraints on specifications, and so forth. The last one in this major group is engineering guidelines. And engineering guidelines is an informative document, often tutorial in nature, that explains how things work and how it functions and how they work and how they should be interconnected and so forth. So that's a very practical standard. There are others, I've listed them here. They're less popular or less used. Registered disclosure documents or public documents that people can post or publicize through SMPTE's mailing and contacts distribution mechanisms. Technical specifications, again, are public committee draft documents. They're used when SMPTE wants to put some information, technical information, maybe an advanced preview of a standard to get public comments for the technology committees to use in the development of the standard. And then there are engineer reports, which are just a report issued by a study group or a technology committee or a task force on a subject of interest in the industry. SMPTE has a lot of liaisons. This is only some. IEEE is on the top of the list. IEEE is closely connected with SMPTE. IEEE is the body that issues and publishes standards for the society. Advanced Television Systems Committee, you may have heard of that. They have issued a lot of white papers and documentation on advanced television systems. Digital video broadcasting, same kind of thing. And then, of course, the World Wide Web and working groups for JPEG and MPEG. These are all liaison organizations. Well, now that we've established why we need standards, as well as the type of documents that are necessary and sufficient to define them, and they're used by the world of engineering, now we'll look at how they're created, the organization and structure. This slide is a cover slide for the standards organization and structure. This is an overall view of the technical committees that actually are the individual bodies that generate standards. There are 10 active committees that you'll see in a moment. Technical committees are staffed with volunteer engineers with backgrounds and experience appropriate to the committee scope, topics, and technology. Meetings of the committees take place quarterly, but communications with the co-chairs of the technology committee and among members is much more frequent. Specific work assignments regarding the committee standards documents are generally made to members at the quarterly meetings. The SMPTE standards work is updated at meetings of all the members, either in person, in the US, Europe, or Asia. But during the pandemic meetings, they have been, during the pandemic meetings have been via the internet for obvious reasons. The meetings are chaired by the standards Vice President, Bruce Devlin, and are very informative. Most meetings were held in, the most recent meetings rather, that were held in September, produced a series of document activities, and information of that of those meetings is included. The general scope of technology committees is to develop and review existing SMPTE engineering documents. Further, to support this work with test specifications and tutorial material for publication in the SMPTE journal. The next slide is the organization chart of the Standards Organization. Standards Vice President is Bruce Devlin up the top, assisted by Director of Standards Development Thomas Bowsey Mason. There are other directors going down the chart. Is my mouse worker? The different groups, sub-chairs, and finally we get to a horizontal row of the technology committees. As I said, there are 10 active committees that are generating standard documents. There's some other working groups that are sub to the 10 committees that somewhat take care of the work, divide the research and drafting of standards. So with that, we'll go to the next group. I'd like to say that this slide and many others here are from the courtesy of Bruce Devlin and SMPTE. These were used at the September update of the Standards Committee, so they are kind enough to let me use them. Just wanted to remark that to attempt to delve very deeply into all the details of the committee's work and their related technology and standard documents in progress would run this presentation until the cows come home sometime tomorrow. So we won't be able to go perhaps as deep into some of them as one that I'm going to focus on later. I therefore will broadly summarize the committees that follow and move on to the last one, the file formats and systems technology, because it is related to SDI. Their work is related to SDI and video over IP and precision time protocol near the end of the selection of section of this presentation. So the first committee is called the Essence Technology Committee. The following slides are basically broken into 4 parts. The first one is on the top left is the TC Technology Committee scope. There's a long explanation. I've given you the short version verbally. The generation and review of standards documents related to electronic capture, generation, editing, mastering, archiving, and reproduction of Essence. You'll hear the word Essence many times associated with technology committees. It simply means video, audio, and data, which might be metadata, might be ancillary data, and so forth. The term Essence applies to all of those together. The topics and standards for this committee are compression, video compression. There are 6 VC1 through VC6, high dynamic range, which many of you have heard of, I'm sure, and reference displays and environments. Reference displays and environments are looking at the viewing environments, measurements and calibration, and standards developed from those topics. The work in progress, there are 5 compression standards in the works with this committee, 4 documents regarding color representation, 1 document regarding metadata, and 1 new recommended practice regarding compression. This committee published 6 standards during the past year. The next committee is called Film Technology. This is an old-fashioned film, and the scope includes the generation of and review of standards documents related to the creation, distribution, and projection of their theatrical film Essence. For your interest, down lower in the top topics, you'll see the B chain responses. I'm not sure everybody knows what that is. I honestly didn't. The B chain there's an A chain and a B chain, not a train. There's an A train and a B train too, I guess. But anyway, the A chain is a soundtrack. There's all be decoders if there is one, and all of the projection related equipment in the theater. The B chain is the power amplifiers, wiring, and speakers, which is vital to the sound. In a big theater with large, massive speakers, the amount of current that's required to drive the speakers is massive. And the wiring is as heavy as an industrial installation or very high rated wiring in a house. Hello? Okay, sounds like feedback. Anyway, the topics and standards for this technology committee include physical film dimensions, film synchronization, and this B chain responses that I mentioned. The B chain is the speakers and wiring and amplifiers. The work in progress for this committee, there are 6 active documents in the works, 4 working groups working on specific applications and recommendations, an ad hoc group working on industry test film maintenance. SMPTE provides test films for the industry, and people can get them. I'm sure that there's a cost involved, but it's now becoming more popular, I think, than it did before. And last year, reaffirmed were 6 documents in this committee. The next committee is digital cinema technology. The scope is the generation and review of standards documents related to the creation, distribution, and projection of digital essence, not to be confused with film in the prior committee. This is not film in a can. Digital cinema is essence sent as an MXF file via internet protocol. The MXS format is used for video, audio, and essence, as well as other data. It is analogous to Apple QuickTime files. Topics and standards. There are 2 suites of standards, standard 428, standard 429, many standards within those suites that define the specs and parameters that govern transport of digital cinema images, basically the audio and data and the video. Those are the images. Digital cinema packaging, interesting term. It's a collection of digital files through store and convey digital cinema, usually again over MXF file transfers. Operational constraints. The Digital Cinema Consortium of motion picture studios, all the big ones, Disney, Paramount, Sony Pictures, Universal, Warner, are all members of that consortium, and they set the rules and regulations and constraints regarding formats, operational constraints. Digital cinema file formats are different than HD. The frame rates are different, aspect ratio, and a few other aspects. So it's not, digital cinema is not just an HD file. And then there's captioning as part of the topics and standards. The work in progress for this committee, there are 7 active documents in the works, many documents under consideration for 5-year review. SMPTE reviews standards every 5 years and documents and updates them as necessary. There was a question that actually came from Marty about SMPTE standards and whether they're ever retired. They are not. They're inactive, but they're still there. I did connect with Bruce Devlin on that question, and he remarked that there was one standard that they were thinking of retiring because he used the term that it was toxic. It was bad, and if people used it, they might get into a lot of trouble. So there's still activity going on how to retire that standard. I don't know what it is. And for this committee, published in the past year, there were three documents. The next group is the Television and Broadcast Technology Committee. There Scope is the generation and review of standards documents related to master essence for television and broadband distribution, including wrapping package, wrapping, and presentation and related topics. The other topics and standards group includes IBID, which is an open binding of IDs. This standard describes an open solution available for licensing, and it uses an interesting method of this distribution of IDs and timestamps called utilizing audio watermarking. This information is sent as audio that's out of the sound range for humans, but can be detected electronically and acoustically. It's not for humans, but maybe dogs can hear it. I don't know. But this is how this information about IDs and timestamps is transmitted. The other topic area is caption carriage, how captions are carried in time code, analogous to advanced vertical ancillary data space. The work in progress, there are 4 active documents in the works for this committee, and published this year, there were none. The next technology committee is Cinema Sound Systems. The generation and review of standards related to sound and cinema B-chain systems and related topics. There is some overlap in technology and topics between some of the working groups, and B-chain characteristics is one of them. The topics and standards, standard 2098, immersive audio bitstream, is also very interesting. A bitstream carries signals to control the theater speakers. The audio bitstream carries audio channels for particular loudspeakers within an auditorium. So they can change the characteristics, I guess principally the volume of the speakers in an auditorium for effects. And of course, that has to be controlled by some sort of file to match the essence of the pictures. And then there's the B-chain characteristics that we just talked about. The work in progress concerns the standard 2098. This is the immersive audio bitstreams with the documents related to the B-chain characteristics. Again, there were no standards published by this committee in the past year. Then we get into metadata, which can be complicated. The scope includes the generation and review of standard documents related to the definition and implementation of the SMPTE registration authority used to identify digital assets and associated metadata. Metadata, very simply put, is data about the data. If you have a data file and there's a need to send information about its structure and so forth, then metadata is sent to take care of that. Topics and standards, the metadata registers. Metadata can be registered with SMPTE. Vocabularies for other technology committees, because metadata is involved in several of those. The website there is there for the registration authority for SMPTE. And then there's the concept of UMIDs. They define a means for providing a method for generating a unique material identifier label to be used to attach to media files and streams. And the work in process, you'll see there are 4 documents that are being worked on for UMID, 2 other documents for metadata registers, and 5 new documents. Published this year was 1 standard. Now we get into files and formats technology. And the scope of this committee is the generation and review of standards documents related to the definition of wrappers and file structures for storage and transmission of all forms of digital content components, The file formats in this committee and the two that follow comprise similar means to move essence and data over IP. While not being intended to be derogatory, when you look at these three committees, the thought of alphabet soup comes to mind when you look at all the possibilities of these. The topics and standards include the MFXF, the material exchange format that we've discussed, DPX, digital moving picture exchange file format, and there are others. The documents in progress, there are 20 related to MFX, DPX, and another one, AFX. AFX is an archive exchange format that was formulated as a wrapper capable of holding unlimited collection of files and metadata related to one another. So that's a relatively new area for standardization. And two new documents are a work in process. Published last year, and from this committee were two documents. Moving on to the next media systems and control services. The scope includes the generation and review of standard documents related to methods of controlling hardware devices and software systems and the management of media workflow processes. The topics and standards include BXF, the broadcast exchange format, and an area called microservices. This is a new area, and there were two new standards related to interoperable master format. That's another file format, IMF, interoperable master format. It is now a worldwide international production and distribution file standard. With these, as I said, SMPTE is trying a new approach regarding standards to get them into the industry for feedback, so the committees can determine where to go next with them. Work in process includes 4 documents in process, 2 new documents. Published in the past year were 2 new documents. So we're almost through alphabet soup here, so we'll go to one more. And the scope for this media packaging and interchange is the generation and review of standards documents related to facilitate interchange and interoperability of formats such as IMF within specific application ecosystems. Based on MXF, the motion picture and television industries have quickly moved to standardize workflows around IMF. Topics and standards include IMF, ecosystems, and Plugfest. Plugfest is kind of an interesting concept. Plugfest are testing get-togethers where people bring equipment and files and so forth to test for plug and play, or maybe plug and not play. And this is done for equipment manufacturers and SMPTE technology committees to gain information for standards revision. It was put on hold because of the pandemic, because this has to be done physically with people getting together. But now it's starting up again to facilitate getting information for standards committees. Work in process, 1 document in maintenance, 2 new documents, and published for the past year, 4 new documents. Now I'll move on to a committee called Networks and Facilities. The number is 32NF. And this is the one I'm going to focus on a bit because of the possible interest in SDI and IP video over some of the other technology committees, although I don't want to shun any of them. Networks and facilities. Network facility 32, that's the number of the committee. VP of Standards Bruce Devlin noted in a recent quarterly standards review, the one in September, the webcast, that if it is a live infrastructure that goes on a cable or fiber, then it goes to this technology committee. NF32 is one of the largest committees in volume of work and in production of standards. They focus on SDI and video over IP in production and post-production broadcast operations. With respect to video over IP, Carl Kuhn's presentation in May covered ST2110 and precision time protocol standards very well. So I don't want to go deeply into them again, except to briefly summarize some parts in case you are not able to see it, but will later provide some recent updates to the standards work in these areas. Video over IP standards review. The first one top is ST 2022-6. In this case, the entire SDI signal is sent in packets over IP. It's an integrated packet standard. Standard 2110, the suite of IP documents for signals sent over separate IP streams. I've shown 4 of them: ST110-10, which is system timing and definitions, -20, uncompressed active video, -30, PCN digital video, PCM, and ST291-1, which is ancillary data. Precision timing protocol network timing has 2 standards that are associated with it. The first is ST2059-1, generation and alignment of interface signals to the epoch, SMPTE epoch. And that's an interesting way to synchronize signals. The epoch is a point in time for timing and synchronization that has been established to be a time at 1970 on January 1st, that time 000000 midnight. TAI rather, time, which is equivalent to International Atomic Time. Signals can be synchronized based on determined timing from the desired signal epoch point and calculations made to synchronize signals. Very interesting concept for that. Much more complicated than Genlock, but nonetheless, it's a way to deal with timing in internet protocol systems. This process, I have to change the subject a bit. This process reminds me of a little bit of a movie called Longitude, shown by Arts and Entertainment some years ago. It's about the inventor of a marine precision clock in the 1700s that can be used to precisely measure time relative to Greenwich Mean Time for navigation to determine longitude. To determine the longitude position gave the captains of ships the position they were at and avoided massive losses at sea. It's a fascinating story. It's a bit like this timing protocol. The ST 2059-1 and 2059-2 standards together are a very sophisticated version of Genlock. I call it Genlock on steroids. So just my little comment there. Genlock is far simpler to use than PDP and has been around for years in analog and SDI systems, but the complexity of internet protocol makes them vastly different. With a sense of humor, Carl remarked that Genlock worked very well, so it had to go. Thought that was quite humorous. Looking at precision time protocol. Precision time protocol is an essential element of video over IP and provides 4 critical functions to IP systems: timing and synchronization, as Genlock does, monitoring of system timing with basic continual checking on key aspects of IP system operation. In that sense, it's a watchdog. The next is an automatic changeover to master clocks for timing, and finally monitoring IP system security, which is quite important. This committee that we're talking about now, networks and facilities, the scope of that committee is the generation and review of standards documents related to defining control of file management, transfer protocols, and physical networks. The current work is focused on SDI and video over IP, as I said. Topics and standards include SDI, Internet Protocol, Precision Time Protocol, and data on AES audio. Also standard 2022, 2110, and 337, which is the transport of digital audio. We'll get to the work in progress and published standards soon. This slide is to give you an idea of the work being handled by this committee. This slide is part of the webcast from the September meeting. It's a bit of an eye chart. So I'll give you just a couple of items. 2 SDI documents, if you go down the left side, and the slug, which is a way that they identify, it's a shorthand way to identify these files. Pretty interesting. Many of these are in a review cycle, and as I said, SMPTE reviews standards every 5 years. The rest of the chart columns really don't add much to this discussion. That's a status of what's going on. It's just an idea of how many standards are in the works at one time. The next chart is similar, and this one has a number of PTP documents, 6. There are 2 security documents in progress. The work on internet security is crucial with respect to the prevention of attacks on IP infrastructure. This group includes work on the IP 2059-15 standard in the family of the others we talked about that relate also to the 2110 suite. A few others are in this list called Tlx Documents, and they're a labeling system replacement for timecode. Timecode's been around a long time. These new documents address timecode, and an audio document, and 2 other new documents. Back to the committee, work in progress. 14 2110 standards are undergoing review and revision. 8 precision time protocol standards, including 2 security documents that I just mentioned, 4 PLX documents, timecode type, and 2 new documents. This committee published 7 documents in the past year. In closing on this particular committee and what they're doing, moving from established SDI systems, hardware, to an IP infrastructure system is entering a brave new world. I think in a literal sense of all 3 words. Brave new world. Therefore, there was ever a time for the need for standards in the world of broadcast. It is now, in the realm of continued development of IP video. The requirements of this new technology are extremely difficult to deal with, and the broadcast and IT engineering world must have up-to-date standards, engineering guidelines, and recommended practices, as well as other documents available. Such documentation is essential for engineers to design facilities, as well as build and test them to ensure that they can provide the best quality video possible. This is a little slide that's a tribute that I think is valid. The broadcast world is deeply indebted to the SMPTE organization and the tireless work of the SMPTE technology committees. I'm now going to move on to a different part of the presentation that's called The Story of the Serial Digital Interface Standard. After about 30 years of black and white television transmission that was based on standard RS-170, that was not a SMPTE standard, where most of American watched Ed Sullivan introduce the Beatles and I Love Lucy episodes, the US introduced color transmission and TV sets in 1954. Slide shows a family gathered around the black and white set. Who's got the remote? And another on the right, an oldie but goodie black and white receiver. Our transmissions in color were NTSC that simply defined in standard ST-170. For this new signal to be compatible with existing black and white receivers, when it was introduced, TV engineers at RCA very cleverly added color by using a subcarrier signal to the black and white signal. Color receivers could see it and display color, but black and white receivers ignored it and displayed monochrome images from the same signal. The RCA engineers made a somewhat subtle change in the frame rate from 30 Hertz to 29.7 Hertz. While the 3.5 megahertz subcarrier doesn't exist in our equipment and transmissions today, its footprint still remains, and we live with frame rates directly related to 29.7. Some of you may wonder why we have a funny frame rate of 29.7. Well, the funniness came because of the introduction of the 3.58 megahertz subcarrier. The early days of NTSC were very frustrating due to technical issues with the TV transmission and instability and drifting of circuits in the TV receivers. Customers had to adjust them frequently to display a reasonably good-looking color, usually based on facial skin tones. NTSC soon earned the nickname, "Never Twice the Same Color." Meanwhile, in Europe, one group of engineers from Germany and the UK and one group in France were working on schemes to add color to their respective black and white existing 50 Hertz systems, pre-PAL and pre-NTSC signals. Neither of these two groups had any confidence in using NTSC scheme for their reasons noted above. Further, there was no practical way to make them the same, mainly for techno-political reasons. Could not see the French and the German having the same standard. The French came up with an FM sequential color and memory system. They called it SECAM. It was quite different, quite complicated signal that made manipulating and processing it very difficult. And further, the images could not even be edited. The SECAM standard was referred to as something extraordinarily contrary to American methods, SECAM. When the PAL standard was developed, that included solid improvements over NTSC. It was termed Peace at Last, PAL. The NTSC standard, SMPTE 170, served us well for the production and transmission for many years. But starting in the 70s, a major revolution in studio television operations occurred. Professional television production and post-production operations embraced the use of digital television technology, included in digital black boxes, sometimes referred to as digital islands, for reasons you'll see in a minute. These islands were used for time-based correctors, frame synchronizers, and early effects equipment. The digital box island looked like this. The box had an input front end that was analog, that accepted NTSC analog as an input, and processing and A/D conversion took place in the first box to convert to digital for digital processing, which is where the actual time-based correction, frame synchronization, other effects took place. And then the signal was converted back to NTSC on the output box. The internal functions inside the black box were rather complicated, and I don't want to go deeply into them, but typically when the NTSC signal was processed and converted, the governing conversion was not standardized, and each manufacturer had its own standards. So every digital black box was different. I think you can see where this is going. The digital processing slide in the middle was dependent on what function was being done, as I had said, TBC, synchronizer, standards converter. The black box trend continued into the 80s. And with more digital processing function and products, including digital video effects, with pictures spinning around and page turns and all kinds of funny stuff. And then graphics equipment, still stores, and standards converters were introduced. Each company producing such products had their own uncorrelated and incompatible digital processing scheme, such as clock rates, signal formats, architecture, compared to the others. Unfortunately, but unavoidably, the input and output analog processing function and the digital islands introduced distortions and artifacts, ghosting, and double images. Passing NTSC through the one box was generally acceptable. But when the islands were cascaded using analog interfaces, as shown in this diagram, that shows NTSC as the interface signal between a string of these islands, the distortions were compounded. And after passing through boxes, the end result was not acceptable, thus losing many of the advantages of internal digital processing. What could be done about this? The problem at this point was international. Both North America and Europe were essentially in the same boat on a big ocean between us and needed solutions, but hopefully on common ground. Further, aside from wanting digital processing of television to advance, both the worldwide engineering community and broadcast product manufacturers wanted to be totally rid of NTSC, CCAM, and PAL. At this point, SMPTE began development of a digital interface to take the place of analog. The term, this interface was based on composite digital. Composite digital means the entire signal was consisted of both luminance and chrominance color. Such signal could be used to connect the boxes. It was a digital signal, but because it was totally based on North American standards, would therefore never be used in Europe. At the same time, the Europeans were thinking about a common digital standard for use in Europe, but they're also faced with the major signal differences between the PAL and NTS and CCAM standards. Engineers in North America and Europe both feared that we could never reach any level of commonality regarding signal parameters, and therefore not create a common digital interface standard. The serial interface, this is what the desired goal was, to take the islands and get rid of the analog processing where the red X's are and use the digital signal to interconnect them. To continue with the story, the European Broadcast Union formed a working group to work this effort. They reached an agreement in 1979 at Montreux that component digital standard, not composite, but component digital standard, meaning the digital signal consisted of separated luminance and color parts, rather than composite digital developed by SMPTE, was the way to go. They also realized that the world community would be best served if there could be an agreement on the single production or studio digital interface, regardless of the color standard. As noted, SMPTE engineers were working hard on the composite digital interface standard, but then rather abruptly stopped work and put their nearly finished standard on the shelf and turned their work toward a component digital standard in conjunction with the European community. It was a somewhat daring decision, but inevitably the right choice. In 1980, they eventually came to an agreement, North America and Europe, on many of the parameters. Stan Barron, whom some of you know, deserves a great deal of credit in bringing this agreement to fruition. Stan worked for me when I was the head of engineering at Microtime in Connecticut. He is an extremely talented engineer and a great pleasure to work with, and he deserves a lot of credit to make this happen. And so, simultaneously, the Europeans generated CCIR recommendation 601. CCIR has now been renamed International Telecommunications Union, or ITU, and simply generated the standard 125M. So CCIR on one hand had 601, simply had 125M. The two documents were essentially the same. They served on the basis, to move forward on generating an SDI standard. There were many meetings in North America and Europe to crunch the numbers, come to agreements on structure and parameters, and achieve the goals to have a standard with many common factors for international markets and applications. It was a winner for both sides and the global advancement of television. The winning result is shown in the lower part of the slide, where the digital signal connects to the digital processor from one box to another without the use of any analog and processing in between. The serial digital interface was born and first standardized as standard 259 by SMPTE in 1989. The initial SDI standard now heads a family of standards that have been introduced to support increasing video resolutions, HD, UHD, and beyond, and different frame rates. 3G SDI, 6G SDI, 12G SDI standards have been published. The next slide is the ancestry of the SDI story. Just going through it quickly, the top is the monochrome standard that started television viewing in America. Then the connection to NTSC color, simply developed that standard. Then the component video interface and CCI recommendation 601, both digital standards, combined to create standard 259 serial digital interface. I show on the left standard 244, which was the composite digital interface that was shelved by the SMPTE committee. The ST259 then leads to the family of standards that I mentioned earlier. And then finally, we have a connection to video over IP and the 2110 suite. So this slide is the unsung hero. This is the BNC and cable that connects SDI to equipment all around the world. So that is the story of SDI. Personally, I consider myself very fortunate to have been a part of this evolution and to have made contributions to it as a member of the technical committees in the 80s, working with sleeves rolled up with some very highly talented engineers from Sony, Grass Valley Group, Panasonic, JBC, FOR.A, Tektronix, and many others. I hesitate to give a list like that because I'm sure I'm going to omit people that should be on it, but they knew who they are and they all made contributions, that's for sure. Also, some chip manufacturers. One was named Genom from Canada, now called Semtech. Semtech bought Genom. There was ADD converters made by TRW They made excellent A to D converters and D to A's that allowed the digital processing to be done cost effectively. And to all the people who worked on it, and they worked on the committee as well. So I thank you for your attention. This image is from the SMPTE website. It's the standards image that I thought was pretty nice to put in there. My email address is there, david.e.acker@verizon.net. Please don't hesitate to contact me if you need any questions answered.
Any
Any
Q&A for?
Yeah, questions? Yeah, that's the next slide. So Q&A, any questions that people have?
David, that was excellent. You may want to unshare for a moment,
Yes, I'm going to do that.
and then it'll go back to full screens.
Okay.
Well done. It was a great presentation. I have
Thank
a
you.
question having to do with the migration from regular SD to HD SDI. I'm still dealing with that in the local cable access thing, where there's still a lot of analog composite around there and a lot of conversions to SDI and HD SDI. And there's some real problems with some of the devices that they say that they will take SDI or HD SDI, but they won't do it correctly or not without some aberrations. So I'm thinking that there are some standards out there. I'm not going to badmouth any companies, but between Blackmagic and other companies that make these converting devices, sometimes they don't do everything you hope they're going to do.
Yes. Some of it is economics. Some of it, companies will take shortcuts and find ways to get around what the standards require. They'll work sometimes, but not all the time. I've seen that happen. You have to follow, especially the SDI standards, you have to follow them to the letter. Otherwise, it just won't work. And when you move from SDI, which was a standard 270 megabits to HD and gigabit rates, and line rates lines are higher, the frame rates are faster. All the HD SDI standards are remarkably different than the initial SDI standard. So you can't take shortcuts with those changes. And I
One of the situations that we're running into is taking the analog output of a Sony digital recorder. It's regular high-end DV cam NTSC video, but it had to go into a Blackmagic device to have the audio embedded so that it would be SDI with embedded audio, and then upconverted through a Blackmagic device to HD SDI to go into a live streaming device by Videon. So these three little cascading boxes did everything they were supposed to do, but by the time you saw the final picture on the screen, there were line artifacts or other aberrations that you didn't expect to be there, and there's no way to fix it.
No, you can't fix that. It's very similar to what I was explaining with the digital islands, that if you have a problem with one box, you get away with it maybe. But if you cascade a bunch of them, it gets worse and worse and worse as you go down the stream. So, and I'm sorry to hear your story, but I'm not surprised. I think that embedded audio sounds really simple, but working at Broadcast Picks, we did a lot of products with embedded audio and worked on them, and they weren't trivial. It's a lot of stuff going on with audio. Audio it's always been the orphan of video. It shouldn't be, but some manufacturers don't pay as close attention to audio as they do with video, and you can't get away with that. It doesn't work.
This whole problem of this conversion and upconversion was superimposed over fighting with a new iMac, and the iMac had just been upgraded to the latest software operating system, and it would either reject the audio or reject the video, or it would dump. So between trying to solve all the regular conversion cascading problems, the device that was doing the live streaming would just up and die. So it was just an orgy of pain.
Yeah, I understand. Well, SDI is a wonderful signal, but it doesn't fail like analog. If you have analog video and the cable is too long or so forth, and the signal loss gets out of the way, the picture gets smaller, or not smaller, but the signal gets smaller and the picture gets affected. SDI doesn't do that. SDI has what they call the cliff effect. It reaches a point where it just stops because it can't take anymore. So that's the cliff. It falls off the cliff, and you don't get much warning when that happens. It's just here 1 minute and gone the next.
Where do you see things going in the future? Obviously there are standards going all the time, but take us out 20 years from now, and where will things be?
That's a good question. That's a good question. I think video over IP is a big factor. There's a lot of pros and cons that I'm reading about it. That it's not terribly cost effective, not initially. And if you have let's say a medium-sized operation, you're not going to tear everything out of there, get rid of all the copper and SDI to replace it with IP. Why? Because SDI works fine. But the thing is that, as you can see from the file standards, the number of file standards for IP is going to be used to carry everything. That the Internet Protocol infrastructure is going to have to support. It's going to have to be faster. There's going to have to be changes in the infrastructure. It has to go above where it can go now in terms of speed, because it's going to get jammed. And I think that's where it's going. But how they get there and it's another story. But SMPTE is doing a tremendous amount of standardization work with IP, and that's where it's going to go.
What I was told is that the biggest bugaboo for sports telecasting with IP signals is the latency issue. That if you're synchronizing multiple cameras from multiple venues, the latency issue is a real bugaboo.
Yeah, I can understand that. Latency is a real problem, and lip sync is the first latency issue that all of us had to face and solve. But there's different ones, different latencies with IP, and this PTP synchronization system is pretty neat. But boy, that is really complicated. Going back to 1970 for an epoch timing point, and then projecting it over time. And then calculating it. Really makes your head swim. Genlock
does.
Plug the black burst in and turn it on.
I think a while back, atomic clocks were adjusted because the rotation of the Earth had changed.
Yeah. Well, it's complicated. You go back to 1970. The time, within a microsecond. Man, that's mind-boggling. It really is. But it works.
Wow. Well, David, thank you. This was an education. I have, to be honest, have not read all my SMPTE journals, even though I no longer get the paper version. I do them online. But I had no idea the depth of all of these standards all concatenating into one. It's a big project.
That's a master project. I did want to add that Bruce Devlin, who's been, I have some other people I want to thank too, but Bruce Devlin has been remarkably helpful to me in getting information and standards and sending the webcast updates and so forth. Unfortunately, I'm not sure the background, but he's going to step down as VP of the Standards Committee end of the year, and he's just a remarkable guy. The depth of knowledge is really, really great. And while I'm at it, I would thank a couple of people at headquarters, Roberta Gorman and for her help in getting standards for me. They've all been extremely helpful to help me get this done. So anyway, I don't know if that answers your question, but
it does for me.
The standards are. It's a remarkable task that we have undertaken as a committee to move forward like this. So
Dave, I want to thank you also. And one of these days, we'd like to have you back and give us the history of the development of the time-based corrector, because I don't know if
Oh,
anybody
really?
better to do
Oh,
it.
I wouldn't mind doing that.
Yeah,
That's an
I
interesting,
used some of your early ones, and they were amazing.
well, that's an interesting story. I'd be happy to do that. Yeah, it would be good.
If
A lot
I
of
can
fun.
tuck in one question at the end, this is Brian Koblars. Question is, in the future, do you see 2110 also beginning to incorporate other aspects of signal transmission, especially internationally when we get into the various privacy issues that are coming up between different countries, as well as building in any protections related to ransomware or other intrusions that could happen to that signal transmission?
Yeah, it would make me nervous. SMPTE is addressing the attacks on the internet relative to this. I think that's going to happen. Unfortunately, there's bad guys, and the bad guys seem to be, some of them, about a half a step ahead of the people who can stop them. So I think that's a real, it's a legitimate concern. So, and also, there's one other person I wanted to thank, and that's my wife for her support while I was doing this. It was a relatively long project, and she had a lot of patience and support for me. So thank you.
And she has a great computer too.
Yeah, a good computer, because mine, I'm still having trouble with that computer. You know, unbelievable. My computer crashed about 4 days ago. There's a lot. I had to replace the operating system, Windows 10. I wiped out everything. I lost everything, but it was backed up. And but it's still a pain to have to download all of your applications and data and so forth. I'm still doing it.
Oh, the manual.
It's that was a trauma for a little while.
David, thank you much.
Okay, you're welcome. I'm happy to do it. It was my pleasure.
Thank you so much. Good night now. Good
Good
night,
night now.
everyone.
Bye.
Watch your email for November's meeting.
Okay, bye now. Take care.
Good night,
everybody.
all.